Yeah.
So let's get started. Today I'm going to talk about this paper archived last week, ZeroNVS, zero shot 360-degree resistance on a single image. As I tried to know this paper, there are two things. So first one is mean motion. That mean to under 360 degrees, and also on the same. So basically, giving any second, then also in the image. Paper before, so it's a parallel. We're also doing 60 degree sequence, but it's considered only on the points of the object that the object single that is that cycle and even about and here that the paper. Sorry. Maybe it's not sorry. Can you hear me?
Change something.
Sure.
So yeah, so maybe just
People on the Zoom. Okay, I think we have to use this one, but I can bring it to this.
Hello? Yeah, is it better?
Okay,
nice.
Great. That's cool. Okay, let's go back.
Cool. Yeah, so basically just two things. One is zero shot, another is a real image. It's considered in the wild data. And so here they show some demos in their papers. So at the left top on those two columns, you can see those just given a single image about the things, and then the models can generalize to any other views, 360 views, and you can consider also it's not only generates the foreground, it also considers the background. And then you can see this motorcycle, it also have some light and some shadows considered. Cool. And there are more examples we can take a look together maybe. And yeah, here you can see given one image, you can rotate this image and getting some cool demos. And also you can, their model, they can consider the indoor settings and also outdoor settings, unbounded things, kind of NeRF 360s. Yeah, only from one single image. Cool. Yeah, those are their experiments. There are some demos. And before we dive into the details about this paper, ZeroNVS, so let's consider its background, this prior work 0123, which is quite popular, I guess. I will just briefly talk about this paper. So the idea is similar. It's also doing the zero shot novel view synthesis, but it's considered only on the object level. So you can see given a object, given one image about one object, and you can generalize to other views. with a quite good results. And even for those unobserved regions, you can hallucinate those regions and given some meaningful in painting. And the idea about this paper is pretty simple. It's trying to leverage the prior knowledge trained on the large language, large diffusion models. And because the diffusion model can already give us quite good results on the 2D, you can generate the 2D photorealistic images, condition on the promote. So why not we just condition on the input view and also the relative camera translations? So this is a pretty straightforward, but it actually works pretty well. So given our goal is to learn this function f, and the f functions is take the Gaussian noise and the input, and it outputs the output view, and it condition on the input view and the relative camera translations. And to train this model, they first grab already pre-trained models, stable diffusion models, and then fine-tune it on the observers. And basically, for each actor, each object is render different views in the Blender, and then you can get in this paired image X and XRT, which is the target view, and also the relative transformation. Yeah, because it only considers the single object, so the translation and the rotation here can be simplified a lot. So in their paper, they only consider the 3D of the camera transition. So it's just theta and phi and the radians r. So basically the difference relative pose can be just by the subtract about the parameters about the input view and the target view. And then they concat those 4 dimensions. They have the sine and cosine for the 5 dimension. And then they concat those features with the clip embeddings and use that as the promote for fine-tuning the diffusion models. And you can getting the good results for this paper. So yeah, this is basically the 0, 1, 2, 3. Any questions for this work?
What algorithm is used to generate that 3D model? This algorithm is producing different multi-view 2D images. And how do they merge all the data together to get a 3D model?
Cool. Yeah, the question is, yeah, I will just repeat the question in case the audience from the Zoom cannot hear that. Yeah, but the question is, how can we get the 3D models? Because here I only do they only do it in 2D. So the answer is the main paper they only consider the 2D stuff. They only consider this conditional generation, and they didn't consider the 3D model. But this can be definitely easy to plug in with a lot of existing network. For instance, you can doing something giving on the input views from different views. You can just reconstruct NeRF, and also you can leverage some like the dream fusions. You can use the front-end SDS, the score distillation sampling to basically distillate this 2D model to the 3D. Yeah, so in their paper, they tried the SGC, which is similar to the dream fusions to getting the 3D model. But it's definitely doable. If you get in the camera image, you can get the 3D models.
And I assume that they get their data sets by first using some large scale 3D model data sets, then take different multi-views. Okay.
Yeah, they take the pre-trained models, stable diffusion models on 2D, and fine-tuning is on the 3D observers, generating quite a bunch of different views and overfitting that, fine-tuning that. Cool. And there are some challenges when applying the 0, 1, 2, 3 model to the in the wild scenes, in the real scenes. So this is primarily because the real world scenes, it can be quite diverse in terms of the many aspects. For instance, the cameras is not object centric, it's not always looking at the center of the object. It can be any arbitrary camera setup and looking at different positions. Also, the scenes can be very diverse in terms of the scales and the backgrounds. You can have very large scenes, very small indoor scenes, and even for the object is and also some small object is also a thing. And for the background, you can have different background. Those are quite challenging. And this paper, they tried the 0, 1, 2, 3D on 0, 1, 2, 3 to directly on the in the wild scenes, but it's not perform good. So the major contribution about this paper is trying to address those limitations. And they propose several minor changes on the 0, 1, 2, 3, but it actually helps improve the performance and getting better results in this setting. So the first, we will go over those details. Basically, just on the camera side is using a more general parameterization. On the normalizations, because the scale can be different, it has some depth-aware normalization scheme, and also they modified the SDS formulation to better handle the background. Cool. Let's talk about them one by one. So for the camera parameterizations, we know that in the object levels, all the cameras is fitting into the object. So it's just pretty simple. You can just subtract the theta phi and the radians r. You can already get the relative camera positions. But this is not true for the real world data. And for the real world, for example, you can see the camera. This is a SLAM setting. The camera is just everywhere. It can be multiple scans. It can be not seeing toward the actors. It can fit in everywhere. And so the more unified formulation for this is basically for the camera, we have the intrinsic and extrinsic. For the extrinsics, it's parameterized by the 6 stop. Basically 3 dimension on the translation and 3 dimension on the rotation. It's raw, pitch, and yaw. And so to do this, they just calculate the relative transformations using the extrinsic matrix. And then also they adding another dimension called field of view. Basically, because they are using mixed source of data sets where the camera is not, can be different, the field of view. So they're doing some normalization on the intrinsic, but it's not fully finished. So they do also consider the field of views.
Sorry, why did they do field of view?
Oh yeah, it's because they are training on multiple source of data. So it's captured by different cameras. The intrinsic is different. Yeah, so they're doing some pre-processing to basically crop the image to be the same size. Yeah, but they also need the field of view to fully condition. Yeah, so this kind of parameterization is, they have a good property. It's agnostic to the rigid transformation. So no matter how you multiply this camera matrix, the relative cameras won't change. So you can prove it easily here. Yeah, but one thing is not, it's not agnostic is the scale. If you scale the things, this parameters, this condition will change also as well. Yeah, so basically they just replace this 3-dimensional to this 6 dot plus 1 parameterization on the condition. And here the M denotes the condition functions. It takes as the depth map, and it also takes the field of view, the extrinsics, and also the source image I and the target image J. Yeah, so basically, this is their formulation. And as we mentioned, there is one thing we didn't answer clearly is how about the scale? If we scale the things, in the real world, we have different data sets with different scales. If the scale is not normalized properly, the distributions we're trying to learn is too challenging. Ideally, we want to learn just normalize all the things into a unit cube, and our camera distribution is similar. So in that case, it's the most easy way. But because the data set can be different, so we also need some technique to scale to normalize the things. So the most straightforward way is doing the camera normalization, which is also widely used, I guess, in a lot of open source code. Yeah, also for the instant NGP, they are doing similar things. So basically, they're trying to normalize the camera pose to the unit cube or something. This is just a heuristic to make sure the thing is properly scaled. And so basically, just calculating the translation component about all the cameras, and then finding the largest one, and then normalize So calculating the f here and then normalize the translation part about the extrinsics. Yeah, and this already can give reasonable results. If no normalization, the performance is really bad. And with this camera normalization, it's already reasonable. And the authors also try another technique called the stereo magnification. This is the papers. Yeah, I think very old papers. They are doing the multi-plane image for the novel view synthesis, I guess. Yeah, but they are normalized. They have some techniques to normalize the things. So they also implement here. So basically, they have assuming that you have the depth map for each image, and then you can calculate the distributions. You can just take the quantile, the 5% of the quantile of the depth image, and you know that you treat that depth as the depth for this image, and then you aggregate all the image, and you take the 10% of quantile, and you get in that value, that depth value as the scale value. You assuming that the thing is mostly at that region, the whole thing, and then you normalize it. Yeah, this is just a simple heuristic, I guess, to normalize the thing. But this is actually the Q is quite complicated to compute. First of all, you need all the depth map for all the views, and you need to aggregate all of them to get in the scale. So and second, even if you add in one single camera or you add in one image, this value will be different. So it's not that stable in the training. So the paper proposed another one normalization called the viewer-centric normalization. So which is pretty simple. It's just taking the view image, the depth. They get it from either from the COMAP or some SLAM. You can get a sparse point cloud, and then you get in the sparse depth map, and then you use the off-the-shelf model to complete the depth, and then calculating the 20% about the quantile about the depth map, and you're getting this QI, which is basically dependent to the viewpoint. And for the condition for the M, you also scale the camera based on extrinsic based on this QI. Yeah.
So, one question. So the depth map is coming from like the sparse one is coming from COMAP?
They are different data sets. So they try 3 different data sets. They provided depth, but the depth source can be different.
Okay.
Yeah.
Is that single view? How do they use Golden?
I think they have the multiple view.
Okay.
Yeah, it's just during
It's in training.
It is in training, not in inference. Cool. And yeah, that is so. And they have some simple toy examples to demonstrate. They are pretty straightforward. So 3 DOF is not enough for the real settings. For instance, here the motorcycles. When you are using a 3 DOF, you cannot model the role of the camera. So it can be different than the real one. And if also the scale has some ambiguities, the depth ambiguities, because one object, if it's small but it's near the camera, is similar. If you only see on one single view, it's the same as the large objects that are far away. Yeah. So and also for the view-centric normalization. So if the original stereo magnification, that paper, it will basically, if you're adding one more cameras, it will change if you're adding, for instance, here the camera 3, the depth is facing the ground. The depth will be quite different than the camera A and camera B. So in the original paper is, in the original, if you're using that aggregation normalization, which is this one, they call it aggregation, it will be affected. It's not super robust. And this view-centric normalization is only conditioned on the input view, so which is more robust. Cool. That's basically some, I think, their techniques to adapt to the real world data. And the third thing in their paper, the third contribution is they are trying to improve the diversities about the background. Yeah, they find that if they just apply the standard SDS, similar as the 0, 1, 2, 3 to get in the mesh, it's not good. Yeah, because you only condition on this input view. If we take a look at the loss functions, so no matter what's the view what's the relative camera pose of the M here, we always condition on the input view. So this somewhat limited our diversity about the output. They find that especially for the background, it's usually just a flat color. It's only a single color. It's not a super diverse. Yeah. So what they propose is also quite simple. It's just you given the input view, you have the diffusion model, and you can just generate the condition on this input view. You can directly sample the views at the other degree explicitly. So this two step is you are first generate this one. It's not during the training. You first for each input view, you generate 3 views. And then during the training, they call this SDS anchor. So this two generated view is like a anchor stuff, a predefined conditioning. And it will, when they train the model, instead of using condition on the input view, they will find the nearest this 3 image, given on the input view, they find the closest view. And they choose one of these 3 image, they call the nearest input image, and then they basically only condition on that to get in the prediction of the noise, and they subtract with the real noise and calculating the SDS loss. Yeah, so this is also, I think, pretty straightforward.
Yeah. It's interesting that how people are trying to get rid of SDS by adding new views that are complete answers or something.
Yeah, right. Yeah, I think this kind of changes is not really consistent. Yeah, because it's not it's basically giving more information on the SDF loss, but it's not. There is no guarantee that the generated one is consistent with the original input in 3D space.
Yeah, I think they chose like 120 degrees Celsius, like from the original input is far enough. So so it covers new parts of the scene that are not overlapping the input view a lot. So that consistency isn't a problem.
Yeah. Cool. And yeah, that's basically everything this paper the new things this paper introduced. So also they are mentioning that for this task is not good with the PSNR because there might be still some minor changes, I guess, in the post. It will cause the PSNR to drop a lot. Yeah, for instance, in this example, I think this is not a good example. In their paper, they have another example. Yeah, but even with just a simple pixel NeRF, which is a plain color, or it fails totally, it's getting better PSNR than the ZeroNVS. Yeah, so that's the reason this paper, they claim that for this task, it's better to consider the LPIPS loss, which are more semantically meaningful. Yeah, because it's too challenging to infer the pose stuff only from one single image. Yeah, and they compare their approach with the existing ones. All those, for instance, on the DTU, all of those NeRF papers, the input is one image, and they are trying to test on the other image. But those images, they are actually trained on they are fine tuning. Those approaches are fine tuning on the DTU dataset, but ZeroNVS is only take directly doing the inference. And you can see in terms of LPIPS, it's better. Yeah, but the PSNR is not super good because there are still can be some misalignment, between the prediction and the ground truth. Yeah, and also they consider the MIP NeRF dataset and some other generalization approach, zero-shot approach. And you can see compared to the naive 0, 1, 2, 3, it's better. Yeah, and which is much better than the pixel NeRF. Yeah, but sometimes pixel NeRF can get better PSNR, but it doesn't make sense. Yeah. Just some random color can give better PSNR. This PSNR actually is quite low. Yeah. Cool. And also they compare with SDF and SDF anchoring. So they do some user study and also show some qualitative examples. And you can see if conditioning on more views is better because you will getting more background in terms of the conditional information. Yeah, but the original standard SDF is just a pure background. Yeah, which is lacks the diversity because those regions are not observed. Yeah, so an ideal model should hallucinate those regions. Cool. And in terms of applications, they show that training on all the data set. Oh, by the way, they train on the 3 data sets and test on these 3 data sets, the head-out set, and also test on some new data set. Yeah. Oh, I see. So here, this is the metrics why they are thinking LPP is better because the pixel nerve, you can see this gray image is PSNR is better than ZeroNVS. Yeah, so NVS is so PSNR is not a good metric for this task. So they are saying that's the argument they are making. Cool. And in terms of the camera parameterizations, they compare with the 0, 1, 2, 3, this 3 dot stuff, and also the 6 dot and the 6 dot normalization, aggregation, and the viewer. And the viewer is the best. Cool. Yeah, that's basically everything. The takeaways is the camera parameterization is important. The normalization is important, and SDF anchor is a little bit better to improve the background diversity. Yeah, and definitely there are some more limitations. It can be 3D inconsistent, and also need to tune the SDS anchor update. Actually, I didn't show the details about the SDS anchor stuff. So they, in their supplementary, they also mentioned that they only update the background regions. So if the depth value is larger than 1, they will update with this one, this SDS anchor. Otherwise, they will just use SDS. Yeah, so, and the geometry quality is limited. As you can see, it's basically just a polygon mesh. It's pretty low fidelity, the extracted geometry from the depth map. And also the misalignment is quite common. And yeah, this is similar as the layer level 3. When the extrapolation, especially when the extrapolation is large, there is no 3D guarantee, and there are some misalignment which cause bad PSNR. Cool.
Yeah, thanks.
Yeah. That's everything for this paper.
What do you mean by misalignment?
Oh yeah, for instance, this example. You can see there are some misalignments. The ground truth view and the predicted views. Although it seems is similar as it's not accurate conditions on the camera.
Yeah.
Yes.
Yeah, but I do agree with them. That's not the problem setting. You don't want to get the ground truth. It's the ZeroNVS is also kind of acceptable. It doesn't have to match the ground.
Yeah, that's true. Yeah. Because it's only one single image, it's hard. It's a hard setting. Yeah.
Yeah.
Cool.
Thanks.
Yeah, thank you.
Thank you. Yeah. Can I copy your slides to the slide deck?
Yeah, sure.
I'll do that. Okay, so for the other paper that we're covering today, it's gonna be a short paper. Okay, it's called NeRF Revisited, Fixing Quadrature's Instability in Volume Rendering. And it's from the Stanford lab. And it was released last week, but it's a NeRF's 2020 paper. Yeah. So the motivation behind this is that standard NeRFs or vanilla NeRF have this volume rendering formula. So in this equation, they try to shoot a ray into the space, and to find the color of that ray, they take sort of a mean over the colors of points along the ray. But because we cannot do like continuous integration on the array, we just can sample points on the array. We need some approximations for the probability of each point on the sample being on the surface or not. So this PJ here shows the probability of being surfaced. So when you do this sum here, you will get the color, you will hopefully get the color of the point that is most likely on the surface, on the first surface that the ray hits. Now, the thing about PJ is that when you want to model it correctly, you have to consider two probabilities. One is density, which is the probability of a point in the space being on a solid object. And the other TU is the probability that the ray shooting from some source has not hit any other solid particles up to that point U. So when you take the product, you find how probable is that your ray hits U as the first surface point that it sees. Now, again, as I said, we just can take a few samples along the point, and we cannot along the ray, and we cannot sum over all the U's on the ray. So the way that NeRF did this is that it takes some samples as Sj along the ray, and then it assumes that between each two sample, the value for density is constant. So that's why it's called piecewise constant opacity. So the model that NeRF uses assumes that the density along the ray is piecewise constant, and then it can simplify this integral by setting tau constant here and get to this sum that we know as the discrete volume rendering formula. So this paper is claiming that if you do this piecewise constant assumption, that means that if we've seen this yellow views, and there's another view, this yellow perpendicular views to the surface, and there's another view that you also have in your training set, but it's close to parallel to the surface. These yellow ones make the piecewise constant assumption, and they don't know exactly where the surface is between two samples that are one after each other. So it's ambiguous where the surface is actually is between these two, and neural networks just model this as a like soft surface between the two. So if you have another ray going parallel to the surface, then it's gonna get values along the ray that are not really on the true surface, and it's gonna sum up these colors that are actually corresponding to another surface, and it's gonna get a blurry color. So that comes from the piecewise constant assumption. Now, this paper is saying that instead of using a piecewise constant assumption between each two samples on the array, we can use a piecewise linear assumption, and the integral will also be easily computable analytically, and this because it's a larger degree approximation of the function, it's not gonna have that much of the artifact for the surface anymore. And if you look at the rendered results between these two, it's really good. You can really see the difference on like thin surfaces or like or like less opaque surfaces that we'll see in the results later. So where the surface is very thin and it's hard to model it with piecewise constant assumption, then this model really shines. And here you just can see the probability density of the surface, and then the transmittance, which is the CDF of that. And you can see for the linear one, it's a much sharper transition between non-surface and surface than the constant one, which kind of gives you this blurry effect of softly transitioning to a surface, to a solid space. Okay, so getting into how they do this, like mathematically. So here they're just assuming that the density is linearly changing between the two consecutive samples, Sj and Sj plus 1. And for each S between Sj and Sj plus 1, we just take a linear sample, a linear interpolation between the density of the first and second samples. So that's their model. Then they put this model into the transmittance equation, which is like the exponential of minus integral of density up to a point on the ray. And they do a bunch of math and show that it becomes this. And it's easy to see why this is analytically solvable, because tau is here a linear function, so the integral would be a second order, and it will be easily computed. Now, if you have transmittance and you also have tau, you can get the probability of the surface, which is tau times this opacity. Okay, so that was the main contribution. Now they also show there is a bonus to using this, and that's the fact that you can now invert the CDF between two samples to find the exact place that is good for importance sampling. So importance sampling tries to sample points given a PDF or a probability distribution between 2 points. You can use importance sampling by inverting the CDF and then just using a uniform sampling as input to that inverse CDF function. But the problem with NeRF's vanilla formulation was that the CDF was not invertible because it was piecewise constant, so it was not smooth and not invertible. This one is smooth, so it can also be inverted. They have a very long proof to show the exact T that you can get from inverting the CDF and applying it to a uniform sample U. Yeah, I will show the proof in the paper if you're interested. Okay, but results. So results are here. Just they're just comparing to vanilla NeRF. And you can see like the boost in the PSNR is not so high. It's just a small boost for all of the like LLFF blender, everything. And for like SSIM and LPIPS is again the same. But I think the main contribution is really shown in the quality results, where there is like thin surfaces like this mesh-like thing here, or like this transparent thin surface on the drum, which is much better shown in the linear model than the constant one. And it makes sense because like it's making the sampling between two points on the ray better, more precise. And here you can see like the same stuff for thin surfaces. Yeah, so that was basically it. So going to show you the proof a little bit. Yeah. So while that's happening, yeah, you can see like the difference between a linear approximation and a constant approximation on this second order function. Like the 2D, like the constant one is not continuous, you cannot invert it. Also like this one was not so like it's not a big improvement, but I think you can see some sharpness happening because of the yeah. It's much better seen with this thin surface. Okay, so yeah, so going to the proofs. I'm not gonna go into all of it, but I'm just gonna give like the gist of what they the gist of what they did. Yeah, so here is the proof for the inverse method, like inverse importance sampling using the inverse CDF. And they basically start from this part. So they say that up to a point on the sample, so they only do importance sampling between two consecutive samples on the rate. So CK is the sum of the probability, surface probabilities up to that starting sample point. And then they say that, okay, the rest of the probability is just the transmittance of the final point minus the transmittance of that point that we're sampling. This is again some equation that comes directly from the definition of transmittance, and from there they just try to solve this equation using normal calculus. But the interesting bit is here, where they have to find this the value for this integral, and they show again this integral can be solved using their linear formulation of density. So yeah, so basically the trick again comes from being able to solve this part to be invertible. Yeah, and then they solve it and invert it. That's basically what's happening here. Yeah, so I think it's a nice method as it can be applied to any volume rendering method to like especially if you have like thin surfaces and transparent ones. But yeah, the boost that you get is gonna be a little bit limited. Yeah, so that was it. I think we're on time. I'm gonna stop sharing. Yeah, if I think we don't have anyone signed up for next week. If you're interested to present, please sign up. Otherwise, I'll be presenting again, which is gonna get a little bit boring, I guess. But if you have the time, please feel free to sign up. And we will decide on the paper later this week. With your help, we can also suggest you some. So don't be worried about what paper I'm gonna present. That part is gonna be easy. We can help you. It's just that you have some time over the weekend or like Friday to read the paper. And the the slides is also optional. You can just talk over the paper itself and do whatever it's best for you for presentation. Okay. Thanks. I think that's all. See you next time.